Hey guys, it's me. So we're going to go ahead and do exam review 2 today. So exam review 2 mainly covers 2 sections, logarithms and unit circle. So this time around, unit circle was pretty rushed. We only had pretty much about a week to cover like everything there. So unfortunate, but it is what it is. So due to that, I do want to do like a different approach this time around. I'm going to try to do like lecturing a little bit. Just go a little more in depth and like try to get you guys to visualize what logarithms and unit circle really is. And as you can hear right now, I am a little sick, so it is what it is. And yeah, consider leaving a like. And yeah, that would help a lot. All right, so logs. So mainly, when we talk about logs, we're looking at like fx equal to log, right? So we'll have like some sort of base here, and we'll have some sort of number. So let's say, okay, so logs. So let's say I had a question here, like fx equal to log of 100. So there's no base explicitly said here, but always know that it's implied that there's always a base log of 10. So we say it's log of 10, log base 10 of 100. So here we can just simplify it. Well, actually, for logs personally, I always change this into an exponential form. Professor O calls this the African way or something. So basically, like we have an invisible equals x. Oops. We have an invisible equals x. So what we want to do is take our 10. So basically, when we do exponential form, we're pretty much getting rid of the log and just keeping the numbers, right? So I'll take the smallest number, so like the base. So we have 10 here, equal to whatever's on the right side. So here we have just x. So we put whatever's on the right side as an exponent. So 10 to the x is equal to what? To this, to 100. So here, I could just say that this is equal to 2. Or if I really wanted to, I could do 10 to the x is equal to, I could reduce 100 into like terms of 10. So this would be 10 to the second power. And so here, I would just kind of cancel out the bases, and we're left with just x is equal to 2. Or you can just visually see it's 10 and 100 here, and then just reduce it to 2. Whatever helps. But yeah, so that's log. All right, so I just want to go over like properties of logs. So we just did like pretty much like the basis of logs. We just turned logs into exponential form, and we solve for x or whatever we're given. So here I want to go over like properties of logs. So let's say I had a problem of fx is equal to, let's say, 1/2 log base, let's say 4 of, I don't know, 16, right? So we had this whole problem, right? So we want to turn this into like a smaller chunk, I guess. All right, let's do let's do log base 4 of, let's say z. Okay, so now I want to turn, let's do 4. So we have 1/2 log base 4 of 16 minus 4 log base 4 of 2. And let's say I want to turn this into a more simplified version of this, right? So what I can do is, so first thing I want to do is pretty much take the coefficient, so whatever is like in front of the log. So I have here 1/2 and I have here 4. I want to turn this guy into an exponent that goes up here. So what I can do, log base 4 of 16, I turn the 1/2 into just an exponent. And here I do the same thing. So I do log base 4 of 2, and I turn the 4 into an exponent, just like that. So now I want to take into account pretty much just like our processes, right? So we either have like adding or subtracting. So here we have subtracting. And so with adding and subtracting, we do like different processes, right? Pretty much this dictates whether this term goes on top or bottom. So when we have a subtraction problem like this, so we'll do log base 4, and we'll take the top term, which this guy is top term. So I have 16 to the 1/2 over, we have 2 to the 4. So this guy just goes 2 to the 4, just like that. So now I want to turn this guy, like take the exponents into account now. So this guy is a little special, he's 1/2, right? So what I can do is just kind of, well, 1/2 is the square root. So imagine I have square root 16, right? So we know that, so this top number 1 is from here. It's the exponent inside of the radical. So there's a imaginary 1 inside. And then for a square root, we know that it's also a little 2 on the outside, like that. So it goes in the order of like, so the top is here, and bottom is on the outside, so 1 over 2. So I just turn him into a radical 16 over z to the 4. All right, this is a z. I wrote that as 2. Oops. Let's do z, and this is also a z. So yeah, so we have log base 4 of radical 16 over z to the 4. This can also be simplified as just kind of log base 4 of 4 over z to the 4. Something like that. So this, I just want to go over like the coefficient, subtraction, and just kind of how to like simplify it. So I guess I can also show like the process of expanding as well. And yeah, that pretty much covers this section. All right, so let's go over unit circle now. So I know different professors teach a different way. I'll start a very different way than the professor I teach under now. I believe Dr. Kaglar teaches only the first 3, like 30, 45, 60. I don't really know what Professor Hernandez did, I'll be honest. But basically, they don't want you to memorize the whole thing. Is their whole like concept. They just want you to know like certain functions, and then like we'll do the opposite of it. I'm gonna do the long way around. I'm gonna go ahead and do the whole thing because this is how I learned it, and yeah, this is kind of just how I want to teach it. So we have just a unit circle, right? So just basically a circle with a XY grid. So we always start with unit circles on this side. This like right x-axis, we call them 0. So 0 has a like, well, let's do angles first, and then we'll do the coordinates. So we do 0. So okay, so each of the like the pegs here, I don't know what we call them, but like kind of think of them as kind of like landmarks, right? So we have 0, then we have 90 degrees, then we have 180, this is 270, and then 0 also becomes 360 when we do a full rotation. So there's like angles in between 0, 90, 180, 270, right? 360. So let's draw 3. 1, 2, and 3. So let's do a little arrow here, another arrow here, another arrow here, and then the last arrow connects to 90. So for this smallest slice we have here, it's pi over 6. Or if we want to turn this into degrees, we can do, let's do over here. So we know that converting from radians to degrees, we do what? So we have radians on top, and we want to end up in degrees, right? So we do 180 degrees over pi. Because this way we can cancel out the pi's from top and bottom, and we're left with just 180 over 6, which this simplifies to 30 degrees. So pi over 6 is just 30 degrees. Next up, our second biggest slice, medium slice, is pi over 4. So again, if you were to do this whole thing with degrees on top and over pi, we're left with 45 degrees. Moving on, we have pi over 3, or this is 60 degrees. And then we move on to this guy, which is 90 degrees, and so on and so forth. So basically, when we do unit circle, quadrant 1 is basically reflected over here, here, and here. It's like the same concepts, but we add on different degrees depending on where we are. So essentially, every angle has its own coordinates. So 0 we have here, it's going to be 1, 0. It's basically saying, imagine I was graphing this out, right? So let's go over here. Imagine I drew a grid, right? So at angle 0, we're basically starting off here, just 1, 0. So this is basically saying that, well, it's a circle, right? So like we just drew a little grid. We're basically saying here is the radius. And the radius of the circle is just equal to 1. we know that with radius, we can't have negatives, so just know that our radius is always 1 at these points. So 1, 1, 1, 1. Well, actually, it would be 1 across the whole board, but yeah, just our radius is 1, and that's why we're starting at 1, 0. So moving on, at pi over 6, we have, so the way I remember like these, the points or the coordinates of the unit circle, I'd use a little mnemonic. It's called sine 1, 2, 3 and cosine 3, 2, 1. So I know you're probably asking, like, what the hell is this, right? So basically, this goes in order of pi over 6, pi over 4, pi over 3. So cosine and sine are essentially our x and y's of, like, when we graph, right? So here we could say, like, this point is what, 1, 0, 1 comma 0. So we could say that our cosine of, let's say x, right? Actually, no, let's not use x. Let's use just good old theta. So cosine theta here is just 1, and my sine theta here is just 0, where cosine is equal to my x, and sine is equal to my y, right? So it's the same thing here. Like, these coordinates are x and y's, where it's just cosine comma theta, or cosine comma sine. So here, at this first point, this is pi over 6, pi over 4, pi over 3. So cosine 3 is just 3 over 2, and this is square root. So first point here is pi over 6 is equal to square root 3 over 2, comma, sine here was what? 1, right? So I have 1/2. You could also say that this is square root 1, but we know that square root 1 is just 1. So it's just left as is 1 over 2. Moving on to 45, we have what? So we start off with pi over 6. Now it's pi over 4, right? Pi over 4 is 2, and we have 2 here. So cosine here is just 2 over 2, and my sine was square root 2 over 2. So moving on to pi over 3, or 60 degrees. So we had here pi over 6, right? So imagine this is supposed to be straight. It's like, 1 over 3, 2, 2, 3, 1, right? So we had pi over 6, pi over 4, and now pi over 3. So cosine here is what? It's 1, right? So here I'll write out 1 over 2, comma, and sine 3. So this gives me square root 3 over 2, like that. So you can kind of imagine with this mnemonic here, like there's a square root over everything here, and then like everything you put down has to be over 2 because that's just how it is. So then we have 90 degrees, which is 0, comma 1. So imagine I was graphing out. Let's say we knew it's a circle, right? And we knew its radius is 1. So we just went from 0 to 1, so it's 0, comma 1. So now we have quadrant 2. So let's go ahead and draw this out. So I have another grid here. We use a mnemonic called all students take calculus. So all students take calculus, where like the letter stands for a function that's positive in this quadrant. So quadrant 1, it's A is equal to all. So here it's positive because these follow along with, like, imagine you're graphing, right? Like we have positive here because that's like a point, let's say like 2, 3, right? So we have 2, 3, it's somewhere here, positive values overall. For S, this stands for sine. So here, imagine we're graphing, let's say negative 2, 3. So negative 2, 3, we have a negative x and a positive y. So here we have negative, positive, and then quadrant, oh wait, I forgot to label the quadrant, sorry. So this is quadrant 1, this is quadrant 2, this is quadrant 3, and this is quadrant 4. So we go in a counterclockwise direction. So we do 1, 2, 3, and 4. So in quadrant 3, the T stands for tan. This only happens when we, like, tan is pretty much sine over cosine. So just y over x. So in order to get a positive value from dividing two things, the two things must be negative, because when we divide a negative by a negative, we get a positive. So this is a negative, negative. C stands for cosine. So here we're graphing in quadrant 4. So like imagine like a point 2 comma negative 3, right? 2 points down 3. So here it's a positive comma negative. So this is like our pretty much our flow chart of the unit circle and how we go in accordance to these points. Like these points will be the same, except we're just changing the polarity. I don't know what the term is right now, sorry. But pretty much just changing the signs according to the graph here. So here, imagine, I want you to imagine like, so this is quadrant 1, right? So we have like our 3 angles, right? Imagine we did like just kind of like a mirror, right? We just kind of flipped it over the y-axis. So here I have what? We start off pi over 6 here. No, let's start here. So we did pi over 3, like our last point in quadrant 3, or quadrant 1. Oh my God. So pi over 3 now starts again here. So we have over 3. We did pi over 4. So now we go over 4 here. And then here is over 6. So if you get the drift here, it's like, you know, we did pi over 6, pi over 4, pi over 3. We did 90. Then we would start again at pi over 3, pi over 4, pi over 6. So now I left the tops blank because they changed in accordance to this. So now things get a little tricky because the problem with like thinking in degrees, right? So like 360, 30, 45, 60, right? Is that it kind of hinders your like ability to like imagine this stuff in like I like to think of it like pizza slices. Like it's like the easiest like visual. So 180 is also equivalent to pi, right? This is like our conversion. Pi is equal to 180, and then the whole circle is just 2 pi. So I want you to imagine, so let's say a pizza, right? Let's say, well, in this case, it would be half a pizza for pi, pizza pie. I don't know. So imagine we're dividing up a pie into 6 slices. We get pi over 6, right? Because if we have 6 slices, we get 1, 2, 3. Wait, no. 1, 2, 3, 4, 5, 6. No. It'd be like, you get my drift. 1, 2, 3, 4, 5, 6. It takes 6 slices to make up pi, whatever, right? So imagine here, right, in terms of like pi over 3, right? So pi over 3 was this big whole quadrant. So now imagine I have another slice of pi over 3. It brings me here. So like if I do like, let's do pi over 3 times 2, right? In order to multiply this out, I would say I put it over 1. I multiply across, I get 2 pi over 3. So here, it's 2 pi over 3. So moving on to over 4, imagine I had 2 slices of pi over 4. So 2 slices of pi over 4, let's do 2 pi over 4. Oh, oops. Basically, 2 slices of pi over 4 gives me 2 pi over 4. This also simplifies to pi over 2. So pi over 2 is just, oh wait, oops, I forgot to do this too. 90 degrees is also pi over 2. It simplifies to pi over 2, so imagine we have a third slice of 3 pi over 4. We get 3 pi over 4. If you get my drift here, I'm just kind of like adding some sort of number in front of the pi's here to like equate where they are in the half, I guess. And then 6, I have 5 slices of pi over 6. Well, basically, okay, so pi over 6 is the smallest like interval, I guess you want to call that. So like pi over 6 here, 2 pi over 6 simplifies to pi over 3. And then like 3 pi over 6 is just pi over 2. 4 pi over 6 is 2 pi over 3. Oh, I just pressed something. Oops. 4 pi over 6 is just 2 pi over 3. 5 pi over 6 brings me here. It's just like pi over 6 kind of like divides itself into like smaller or like, whatever. It's like, don't worry about that. Don't worry about that. So let's just do the points, right? So for pi over 3, right? So let's do the points for 2 pi over 3 now. So pi over 3, I had 1/2 comma square root 3 over 2. So let's do the same thing. We have 1/2 square root 3 over 2. But now let's check the all students take calculus chart, right? So in quadrant 2, what are my values? I have a negative and a positive, right? So negative x value, positive y value. Here, I have 1/2 comma square root of 3 over 2. So let's slap on a negative. And now he's perfect. Moving on to 3 pi over 2, we have what? We go pi over 4. Wait, no, what did I say? Sorry, 3 pi over 4. If we go back to the pi over 4, we have what? Square root 2 and square root 2 over 2. So let's go ahead and write that down again. Square root 2 over 2, square root 2 over 2. Boom. And now we knew that in the quadrant 2, our x values are negative. So just like that. 5 pi over 6. Let's go back over here to pi over 6. We have square root 3 over 2, comma 1/2. Square root 3 over 2, 1/2, and slap on a negative. So, sine 1, 2, 3, cosine 3, 2, 1. It gets a little tricky now. Maybe I'll just do it now. So basically, right, so let's go in order again. So the pi over 6, pi over 4, 1/2, right? So we did like pi over 6, pi over 4, pi over 3. Okay, so things get a little tricky. So here I went like in order, pi over 6, pi over 3, right? So imagine it's like cosine 3, 2, 1. And then once I cross over into quadrant 2, I restart back at the end, or wherever I ended off, right? So I did 3, 2, 1. Now I'll do 1, 2, 3. Now, I don't know if that makes sense, but just kind of follow along, right? So we did here cosine 3, 2, 1. Come over here, it's 1, 2, 3. But just keep in mind like the negatives if need be. Okay, so now it's quadrant 3. So let's do another 3. 1, 2, 3. And so now, imagine we did here, we like kind of like flip this over here. Actually, is there some sort of... I hope that's like okay to see. Well, whatever. So we did here, we flipped this side like a mirror, right? So now imagine it's like this, but now flip down, if you get my drift. So here we start off with over 3, but now here we start off with over 6. Over 6, over 4, over 3. Because we just flipped this down. It's kind of like a mirror. Like every axis is kind of a mirror to whatever side it is. So like here we just flipped over the y-axis, here we flipped over the x-axis, and over here we'll flip back over to the y-axis and complete the whole run. So over 6. So now we crossed over the threshold of pi. So I want you to imagine, right? Imagine pi plus pi over 6. So if I do that, pi plus pi over 6. So I want to like make pi in terms of pi over 6, right? So what I can do is multiply the 6 to top and bottom. So we have 6 pi over 6 plus 6 plus pi over 6. And this will give me 7 pi over 6. So this guy is 7 pi over 6 because this is just pi plus 1 slice of pi over 6. If you get my drift here. So let's do pi plus pi over 4. What do we get? We get 5 pi over 4 because a pi is 4 slices of pi over 4. Put one more slice and we get 5 pi over 4. Same thing with over 3. We get, this should be 4 pi over 3 because it takes 3 slices of pi over 3 to get to the pi, plus one more slice, 4 pi over 3. 270 is also just 3 pi over 2, or 3 pi over 2. And his points is 0, comma, negative 1. Oh, sorry, I didn't even do this one yet, sorry. So pi is just negative 1, comma, 0. Because imagine I was graphing, again, just, so we did like 1, comma, 0, 0, 0, comma, 1. Now it's just negative 1, comma, 0, because now we're on this side. And now 270 was 0, comma, negative 1. So here, this is 0, comma, negative 1. So now, in quadrant 3, we check here, we have what? Negative, negative, right? So now I want to bring bring the points down once again. So here I had what? This was negative square root 3 over 2. Now make the 1/2 negative. Now I'm left with this. 5 over 4, I have what? Negative square root 2 over 2 and square root 2 over 2. Negative square root 2 over 2, negative square root 2 over 2. 4 pi over 3 is just negative 1/2, and a negative square root 3 over 2. All this is just kind of repetitiveness of like, we're literally just repeating quadrant 1 over here, repeating quadrant 1 over here again, but just changing the negatives. That's really all it is. So now I got to draw another 3 here. So 1, 2, and 3. Okay, so now, again, we're flipping this quadrant over to here. So we're just bringing like our over whatever it is to here. So here I start off with pi over 3 once again. Over 3, I do over 4, and then over 6. Okay, so now things get a little hairy. So we know that a full rotation is 360 degrees, or 0, or 2 pi. This guy's a man of many names, I know. So 2 pi. Imagine 2 pi minus 1 slice of pi over 6. So let's do 2 pi minus pi over 6. So again, if I want to subtract this guy, I have to put 2 pi in terms of pi over 6. So let's multiply 2 to top and bottom, and we're left with, what is this, 12 pi? 12 pi over 6 minus pi over 6, and we're left with 11 pi over 6. 11 pi over 6. This guy, 2 pi minus 1 slice of pi over 4, and we're left with 7 pi over 4. Hopefully you get that right. So if I were to do 2 pi in terms of pi over 4, I would do 8 pi over 4. Minus 1 pi over 4, 7 pi over 4. So 2 pi minus 1 slice of pi over 3 gets me, this would be, what is this, 5 pi? 5 pi over 3. And so again, I want to transfer the points over once again. So here, in quadrant 4, we have what? We have a positive and a negative. So let's start off with 5 pi over 4. We're left with, what do we have? We have positive 1/2 and negative square root 3 over 2. Because what? Imagine I was graphing, right? I have, let's say, a point 2, 3. Or no, this would be 2, negative 3. 2, 2, negative 3. So here I have a positive x, negative y. 7 pi over 4. We have, oops, this is positive. We have positive square root 2 over 2, comma, square root 2 over 2. Negative square root 2 over 2. 11 pi over 6, we have, this would be square root 3 over 2. This is kind of conflicting. Let's just erase that, I guess. Oops. We have square root 3 over 2, comma, negative 1/2. Cool, and that's our unit circle. So I know it's a lot. It is a lot, but I mean, in the worksheet, we literally had just a chart. Like, this is, that's crazy, right? So I'm hoping this, like, drawing out the whole unit circle kind of helps in terms of visualization. I would love if you were able to understand, like, how to plot the angles in the recording, like, quadrants, just knowing, like, our checkpoints and stuff. But I'm hoping, like, I just kind of, like, drawing it out kind of helped, because, yeah, that was a nightmare. So, yeah, this is pretty much unit circle, and we'll do a lot more with, like, the problems on the, like, exam review and stuff, and hopefully that can, like, kind of, like, get it to you. So, yeah, that's it. All right, so we're starting out with a bit of a banger here. So this is chapter 6, so this is second page, question 3. So we're going to start off with graphing here, because somehow this is, like, one of the first questions we have. So, question 3, we have f of x is equal to negative 2 to the x plus 4 power minus 3. Minus 4. Okay, so let's start off with the usual, right? So what's our parent function? our parent function, so this is a exponential graph, so our parent function here is just parent f of x equal to 2 to the x. Just know that in future reference, it's not always going to be 2 to the x. It could be like whatever number here and just whatever to the x. That's our parent function. So like this could be like 3 to the x, 4 to the x, 5 to the x, or whatever the case. But 2 to the x is the most simple one because it's just 2, right? So let's take our parent function here. So what points I'd like to take is just a negative, a 0, and a 1. So let's do our xy table here. Hopefully you guys can see this. This would be kind of a shame. So let's do negative 1, 0, and 1. So 2 to the negative 1, we know that when we have an exponent or negative exponent, we have a fraction, right? So it's always 1 over something. So 2 to the 1 power is just 2. So this is 1 over 2 because the negative gives me a 1/2 or a 1 over something. 2 to the power of 0 gives me 1. We should know by now that any number to the power of 0 gives me 1, no matter what. It can be 3 to the 0, 4 to the 0, 100 to the 0, and we'll get 1. So let's do 1 now. 2 to the 1 gives me 2. There we go. So we have, let's say this is a negative 1. So we have negative 1/2, 0, 1, and 1, 2. So connect the dots, and we're looking at something like this. There is an asymptote here at y equals 0 because there is no way we can hit 0. Because, as we see here, 2 to the power of 0 gives me 1. And then if we go negative, it's just always 1 over something. And we can never hit 0 because basically it's like 0 divided by 0 is just undefined. There is no realistic way to get 0. So we have it as an asymptote. So y equals 0, and that's our whole logic behind why it is. So moving on. Okay, so we all know our transformations, right? So we always have our parent function, then we have horizontal shifts. Then it's going to be, I want to say stretch or shrink. Stretch, shrink, and then we have reflections, and then our vertical shifts. Yeah, that's totally English. Okay, so for the transformation we have here, so let's go through the graph. We have negative 2 to the power of x plus 4 minus 3. So start from the left. This negative means what? It's a reflection over our x-axis, right? Because pretty much this changes our x's, and then, or this changes our x's inside the parentheses, and then this negative affects our y's. So we're reflecting over the x-axis. So moving in, we have x plus 4. Well, the x is part of the parent function, but the plus 4 means what? We're moving 4 units to the left because that's just how it goes. We do the opposite of whatever's inside the parentheses. And then our minus 3 here is 3 units down. So if we draw along the chart, we have horizontal first. So do we have a horizontal shift? Yes, we do. So we have horizontal shift. What is that like? We have 4 units left. So our graph looks like f of x is equal to 2 to the x plus 4. Cool. So let's go ahead and graph this guy out. So in a horizontal shift, right, what values are changing? Like what x value, or what's changing? Our x values or our y values? It's our x's, right, because we're moving horizontally. So we keep our y values from this chart, and we bring it over. So we have 1/2, 1, and 2. And then what's changing? Our x's, right? So if we're moving 4 units to the left, what's happening to the x's? We are subtracting 4. So negative 1 minus 4 gives me negative 5. 0 minus 4 gives me negative 4. And 1 minus 4 gives me negative 3. Oh, that's horrible. 1 second. 1 and 2, right? Yeah. So our new points are negative 5, 1/2, negative 4, 1, and negative 3 and 2. So -5, let's say it's here, like in the middle. -5, 1/2. -4, 1. And -3, 2. Connect the dots, and oh, that is not connecting dots. Hold up. -5, 1/2. -4, 1. -3. We're looking like something like that. And our asymptote. Did our asymptote move? No, right? Because it's just this is a horizontal asymptote, so it didn't move. This is y equals 0. Cool. Moving on. What do we have? We have well, first off, do we have a stretch or shrink? No, right? Because there's something here. Moving on. Reflection. Do we have a reflection? Boom. Yes, we do. So we said earlier this reflection goes where? Let me move this graph up, actually. I don't have space for the fourth one. So we have reflection. But over what axis, though? We said it's over the x-axis because this negative on the outside is meaning we're affecting our y values. If it was on the inside here, we'd, well, I guess this isn't the greatest graph. Well, actually, yeah, it is. It would be up here, like 2 to the negative x plus 4. This would be affecting our x values, but on the outside, it's affecting our y values. So we're moving over the x-axis. So reflection over the x-axis, and our function looks like f of x is equal to -2x plus 4. So let's go ahead and graph this guy out. Maybe a little too big, actually. Hold up. Let's do here. So again, with our table, let's do x, y values. So we know that it's reflecting over the x-axis. So we know that our y values are changing, right? So let's keep our x values. So we have -5, -4, and -3. So what happens to the y values? They're turning negative. So 1/2 becomes -1/2. 1 becomes -1, and 2 becomes -2. -2. Jesus. -2. Okay, cool. So let's graph this guy out. -5, -1/2, boom. -4, -1, -3, -2. Connect the dots, and we're looking something like that. Again, our asymptote did not move because we didn't move vertically yet. Y equals 0. Yeah, next part right. So our last one is what? It's our vertical shift, right? So we have a vertical shift. Vertical shift. How many units? 3 units where? The -3 gives me negative, or units, 3 units down. So 3 units down. Our graph looks like what? Should be just like that, right? So -2 to the x plus 4 minus 3. Let's draw a little grid. Little xy table, and we're in business. Okay, so again, so vertical shift is moving what? Our x's are our y's. It's our y's, right? So again, I'm gonna keep our x's. So -5, -4, and -3. So what's happening to our y values? They're moving down, right? So we have -1 and -1/2 minus 3. This gives us -3 1/2. All right, what about -1? -1 minus 3 gives us -4. -2 minus 3 gives us -5. So let's go ahead and graph this guy out. -5, -3.5 is like, I don't know, here. -4, -4, then -3, -5. Connect the dots, and we're in business. Okay, so what about our horizontal asymptote, though? They move down, right? Because why? We also move down. So this, let's just say this is like 3 here. Boop, 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 boop. Y equals -3 because we moved with the vertical shift. Cool. And let me make sure I know what the hell I'm talking about. Let's check the answers here. What question is this? Number 3. I want to say I'm right. I don't know what the hell I'm looking at here. Oh yeah, I'm right. So, yep, perfect. All right. So for number 4 of chapter 6, we have express as a single logarithm. Assume all variables are positive and b cannot equal 1. So this is question A, 4a. So we have 2 log base b of t minus 4 over 5 log base b of s plus 1/3 log of b of v minus 4 log base b of u. Okay, so basically what we're trying to do here is just kind of compress everything into one logarithmic function, right? So let's go one by one. So we have log base b, log base b, log base b, and log base b. So now we know that we can unlock our special little thing. We can just write log base b here and then kind of compress everything into one single function. Well, actually, before we do that, let's go ahead and just move the coefficients into our exponent slots. So let's go ahead and erase this. Well, I didn't even need to erase that, actually. Okay, so let's go ahead and move the coefficients to our exponents. So we have log base b of t to the power of 2. We have log base b of, what is this, s? Of s to the power of 4 over 5 plus log base b of v to the power of 1 over 3 minus log base b of u to the power of 4. Okay, now let's go ahead and write out that one log, so log base b of, so let's go ahead and find out what goes where, like where on top and where on bottom. So this first term is always on top because that's just how it is. So we move our t to the second, or t squared, to the top. Let's write out big old fraction here. Okay, so then we have minus log base b of s to the 4 over 5. So we see the minus straight down. So these fractions mean they're a radical. So let's go ahead and draw a radical first. Let's put s in here. Okay, and now we have what? 4 over 5, right? So the 4 goes inside the radical, just like out here. This is kind of like a little exponent inside the radical. So we have 4, and then we have a 5 on the outside of the radical. So s 4 to the 5. Plus log base b of v to the 1/3. So this guy goes up here, v. Well, actually, I just draw the radical first. Oops. So let's draw the radical. You can draw the dot here if you want. So let's draw a v to the inside. So 1 here, we don't really need to write the 1 here because 1's already implied inside the radical anyways. So we can just draw the 3 out here. And then we have, what is that? 4 log base b of u to the 4. So we see minus. This guy goes straight to the bottom. Let's draw the dot, u to the 4. And there we go. That is question 4 of chapter 6. Just this ugly looking thing. Yep. All right, and so for question 9, we have, well, it's a 2-part question, but just find the exact value of the logarithmic expression. Do not use a calculator. So I cherry picked like the easiest ones to do because frankly you won't see the other ones because like those are like calculated questions kind of. Well, I guess before this, you're supposed to leave them with like what's the word? Calculator ready form. But frankly, I don't think you're gonna see that, so don't even worry about that. So let's go ahead and do like the easy ones. So this is 9a. We have log base 3 of 1 over 27. So again, right? I would always try to rush to like put the logs into exponential form because frankly, I don't like logs, and exponential form just kind of eliminates the logs. So again, right? There's always a invisible equals x to the side. So I do 3. So we always take the base. So 3 to whatever's on the right side. So here we have an imaginary x. 3 to the x equals to 1 over 27. We could just kind of like raw dog this and just like, no, it's like 3, or 27 is like a base of 3, or we just write this out into terms of 3. So 3 to the x equals, so 27 is a factor? I don't know. No, that's not a word. Anyways, the 27 comes from 3. Like 3 times whatever by itself equals 27. So this, in the case, it's 3 times 3 times 3, right? Because 3 times 9, or oops, 3 times 3 equals 9. 9 times 3, 27. So it's just 3 to the power of 3. But it is a fraction, so it comes like that. Or if you want to write this out, you'd be like 1 over 3 to the power of 3. But the negative 3 is like more optimal. So here we have the same bases of 3, so we just kind of cross them out, and we're left with just x is equal to negative 3. Simple, right? Let's do 9b. We have log base 5 of 1 over square root 5. Okay, well, this is that's kind of an ugly one. Okay, but let's do this again, right? So again, we have an invisible negative equals x, or not negative, oh my god, equals x to the right side. So let's do base 5 to the power of x is equal to 1 over radical 5. So 5 to the x is equal to, so if we want to write this out as a base of 5, we do 5. So it's a fraction, right? So we know it's negative. But what does that radical 5 or the radical say? This is a 1/2, right? So this is 5 to the negative 1/2. Because the 1/2, like 5 to the power of 1/2 is just radical 5, and then the fraction makes it a negative. So 5 is 5 to the x equals to 5 to the negative 1/2. Same bases, so we cross it out. X is equal to negative 1/2. Yeah, that makes sense. Okay, that's 9a and b. Okay, and so we had number 14. I'm gonna do part A. So we are given a function, f of x is equal to log base 2 of negative x plus 2. Okay, so again, what's our parent function here? It is going to be just log base 2 of x, right? So parent function log base 2 of x. And f of x is over here. F of x is equal to log base 2 of x. Okay, so usually when we plot points, right, it's always going to be like some sort of like negative, 0 to 1. But for logs, it's a little different because we choose our y values, if that makes any sense. We'll see here. But so here, let's do negative 1, 0, and 1. So remember how I always said, like, I always switch logs into exponential form? So here, let's do this, right? So we have an imaginary, I guess here would be y, because we have an x here. So imagine it's like 2 to the y equals x. And we have our y's here. We did a negative, a 0, and a 1. So here, let's do 2 to the power of negative 1. Gives me what? 2 to the negative 1 gives me 1/2, right? So our x is equal to 1/2. What about 2 to the 0? We get 1. And what about 2 to the 1? We get 2. So let's plot this out. We get what? So 1/2, negative 1, 1/2, negative 1, 1, 0, and 2 to the 1. So connect the dots, and we're looking something like that. There is an asymptote here at x equals 0 because we would never hit them. Pretty much like it's impossible to get a 0 here because here when I did a negative, I got what? A fraction. And when I got 0, I got a 1. So there's no possible way for this x to be equal to 1 or equal to 0 because it's literally impossible. Because if we go negative, like more negative we go down, we always get a fraction. It's always 1 over something. And we can't get a 1 over 0 because undefined. So 0 is out of the equation. So x equal to 0, asymptote here. So what's our transformation? Well, here, let's go in order, right? So log base 2, that's our parent function. Negative x is what? It's a reflection over the y-axis because it's in the inside of parentheses. It's only affecting our x-axis. And the plus 2 is our horizontal asymptote, or not asymptote, horizontal shift because it's inside the parentheses and something out here. So if we follow the little flow chart, right, we always go to our horizontal shift. Jeez. Horizontal shift. Where are we going? So we have a +2, right? So that means we're going 2 units to the left. So our function here looks like what? It's going to be log base 2 of x plus 2. Boom. Let's go ahead and do our xy table again. Again, right, with horizontal shifts, what's moving? Our x's or our y's? It's going to be our x's. So to keep our y's, we have -1, 0, and 1. Okay, so what happens to our x's here? We're moving 2 units to the left, so that means we are subtracting by 2. So 1/2 minus 2 gives me 1 and 1/2. 1 minus 2 gives me -1. And 2 minus 2 gives me 0. Cool. Let's graph this guy out. So we have, wait, is that right? Hold on, whoa. Oh, wait, I moved this guy, oops. So it's -1/2, my bad. So -1/2, let's say it's like around here, -1/2, -1, -1, 0, and then 0, 1. Okay, that's a really bad graph, but bear with me. Let's go ahead and do that. And then, what about horizontal asymptote? Did he move with the graph? Yes, he did. So here, it's our vertical asymptote. So he moves with our horizontal shifts. So here we move 2 units to the left. So our horizontal shift also, or horizontal asymptote, no, what am I talking about? My vertical asymptote also moves 2 units to the left. So here it was x equals 0. Now it's x equals -2. X equal to -2. Cool. Moving on. Our only transformation is left is our reflection. So reflection, but over what though? We said it's over the y-axis because what's happening here? Our negative is inside the parentheses, so that means our x values are being affected. So it's like a little opposite, like yeah. So our x values are changing, so our x values are, x values are changing, so it's y-axis. If it's outside, our y values are changing, so that means it's our x-axis. I know, it's a little weird, but yeah, so y-axis, what's our formula here, or what's our function? It's going to be log base 2 of -x plus 2. Cool. So we said again, what's changing in the our here is our x-axis, or Jesus, our x values are changing, right? So we're going to keep our y values the same, -1, 0, and 1. So when we have a reflection inside here, what's happening here? They're pretty much just getting a -1 like multiplied to whatever here is, right? So here, 1 and 1/2 times, or -1 1/2 times -1 gives me a positive 1 and 1/2. What about -1? It becomes positive 1. 0 times -1 gives me 0. So let's go ahead and graph this guy out. We have 1, 1 and 1/2, -1, 1 and 1/2, -1. Let's put here. So let's draw this guy out a little more. Let's say it's like here. -1. We have 1, 0, and 0, 1. Let's go ahead and connect the dots. And we're looking like that. So here, where's our asymptote? What happened to him? He also moved. So here, let's say roughly here is our x equals 2. And that's it, folks. This is a pretty easy one, but what I want to get out of this one is like knowing our general shape of our logs. So earlier, I did exponential, right? So log has this like more positive like side because our domain, we can't go negative because there's nothing here that's negative, right? So it's like an outward graph. I don't know what to explain it, but like exponential graph looked like what? It was like this, right? And we don't touch this y equals 0. Our log graph is like the opposite. It's like this. If that makes any sense. Asymptote here and asymptote here. So what I just wanted to go over was just like the general shape of our logs and exponential graphs. because you will be seeing one of them. So, yep, that's it. Okay, so now we begin the fun stuff. This is chapter 5. I'm doing some easy stuff, like just converting radians and degrees. So this is number 1. So number 1, this is A. So on A, we have 480 degrees. So I want to convert 480 degrees to radians, right? So how do we do that? We always use the 180 to pi, right? So if I start with degrees and I want to go to radians, I always put whatever I want to cancel out. Well, actually, no. I put whatever I want in the end result on top. So here I start off with degrees, right? And I want to end off with radians. So I put radians on top, degrees on bottom. So degrees cancel out. Here we're left with 480 degrees. Oh, oops. 480 times pi over 180. So here, I mean, this will simplify to some crazy number. Okay, let's see. I always start some stupid shit. I always do like divide by 2 over and over again. So this becomes like 240 pi over 90. Let's do another 2. This becomes 120 pi over 45. This is probably like over 5. Oh boy. 10, 20. Is that like 24, I want to say? 24 times 5, 120, yep. 24 over, what is that, 9? Does that go any further? 8, I think? No, by 3. It becomes 8 pi over 3. 8 pi over 3. That looks about right. No. Yeah, that looks about right. So this simplifies out to 8 pi over 3. I don't feel like checking my answers, so you do that. Let's do number 2. So I have 2b here circled, so let's do 2b. I have 9 pi over 10. So I want to convert the radians into degrees now. Okay, well now what? So now I want to put degrees on top, right? So I do 180 degrees over pi. So here the pi's cancel out. Multiply across, so I have 9 times 180 over 10. Let's go ahead and cancel out the 10s. So just cross out the 10 and the 0. So I'm left with 9 times 18. Okay, let's see. So 18 times 10 equals 180. So 180 divided by, or 180 minus 18 gives me like 162, I want to say. Okay, let's move on to number 3. We have find the radian measure of the central angle of a circle of radius r that intercepts on arc length of s. So this is really just saying we're using s is equal to theta r, right? So s is equal to our arc length. Our theta is equal to our angle measure, and r is our radius of the triangle. So this is a triangle measure in the end. So they gave us that r is equal to 5 meters. And s is equal to 2 meters. So if I were to put this all together, so I plug it in, so I have 2 is equal to theta r. Theta is r, oops. Theta is 5. So if I want to find this out, I'd have to do this formula, right? 2 is equal to theta over 5. Theta times 5. Simplify this to divided by 5. So our theta is equal to 2 over 5 radians. Okay. I guess I can do 6 too while I'm at it. So 6. This is find the length s. Round the answer to 3 decimal places. This is a calculated question, but we do like our, what's it called again? Calculated ready form. So we just put whatever into one simple answer. So let's draw out this triangle, something like that. I know the picture's bad. 35 degrees, we have 4 feet, and we have s. Okay, cool. So we know that s is equal to theta times r, right? So s is equal to r theta. S is equal to r, so 4 here is the radius, and our theta is 35 degrees. 35 degrees. I believe I think we do have to change this degrees into radians. I think this is a radian only question. So let's do it. 35 times pi over 180. Oh boy, this is gonna be some crazy answer here. Let's see, what is that? 35 pi over 180. Okay, so let's start dividing this. So if I divide by 5, what do I get? What do I get? What do I get? Oh boy. I think I get 36 on the bottom divided by 5. 36 times 5 is 180. Yep, that sounds right. 35 divided by 5. 7 pi over 36, something like that. Let's... Well, I'm not even done yet. Oops. So I take that and multiply this. So S is equal to 4 times 7 pi over 36. So S would be equal to 28 pi over 36. Let's double check the answers. What question is this? 6. They gave me 7 pi over 9. Okay, so what do they do here? So yeah, they just simplified this into terms of 4. So 28 divided by 4 gives me what? 5 times 4 is 20. So this gives me 7 pi on the top, and then 36 divided by 4 gives me 9. So 7 pi over 9. Yep, sounds good. And then I'll keep doing the other questions. Okay, so this is chapter 5, number 8. So we're given a clock, right? A little diagram of a clock. We have our minute hand at 12 and our hour hand at 8. So pretty much imagine this, something like that, right? So the main thing I want to do here is, we know a circle is what? 360 degrees, right? So 360 degrees. And how many subsections do we have? We have 12 sections of the clock, right? So here we do 36 divided by 12, and we get what? 3. So it's 3. This is 1. So we know that 1 hour is equal to about 3 degrees, or pi over 6, right? So if we have an angle between 12 and 8, we pretty much have what? We have 4 hours in between, right? So we have 4 sections. So if we do 4 times 30, so 4 hours times 30 degrees for each hour, we get what? 120 degrees. Or we have to do pi over 4. No, what am I doing? Oh my god. This is 4 times pi over 6. We get 4 pi over 6, which reduces to 2 pi over 3. Let's double check the answers. What is this again? What question is this? 8? Yeah, so they gave us 120 degrees, or in radians we have 2 pi over 3. And so this is chapter 5, number 9. So we are given a triangle. So let's draw this out. Triangle. We are given point B here, point C here. We have a right triangle, A. We're given theta here. Point AC is given 5, and BC is 7. Okay, and we're tasked to find the tan of the theta here. Okay, so what do we know about tan? Number 9. So tan is equal to what? Tan theta, if we don't know anything, we just know it's what? It's opposite over adjacent, right? Because SOHCAHTOA. Let's write it out. Loud and proud. SOHCAHTOA. So we're using TOA. So opposite over adjacent. Cool. So from this point, right, what is opposite and what's adjacent? So if we go opposite, we have 7. So tan theta is equal to 7. And what's adjacent? Adjacent is just 5. So tan theta is just 7 over 5. I guess I'll just segment into 14 here. Might as well. So 14, I'm just going to do all the points, I guess. The most important thing from 14 is these formulas, right? We have, I'll be honest, I don't know what these are called, but I'll just write up all the formulas here. So we have, the most important one I want you to know is just sine squared theta plus cosine squared theta is equal to 1. And from then on, we can just kind of derive the whole thing, the other trig functions. So here we have sine squared theta plus cosine squared theta equal to 1. So imagine I for each term, I divided by sine squared theta. So divided by sine squared theta, sine squared theta, what do we get? Sine squared theta divided by sine squared theta equals 1. Cosine squared theta, so basically the thing I want you to know is cosine over sine is equal to what? It's equal to, what's his name? Cotangent. Cotangent squared theta equal to 1 over sine squared theta. 1 over sine is cosecant. Cosecant squared theta. So now imagine instead of sine here, I divided by the other guy, cosine. Okay, so sine squared theta over cosine squared theta gives me sine over cosine is just tangent, right? So we have tangent squared theta plus cosine divided by cosine gives me 1 equal to 1. 1 over cosine is just secant. Secant squared theta. So these are like our three, oh my god, I don't even know their names. But some formula we use. It's not Pythagorean theorem, I know that. But yeah, these are like what 14 is asking us for. So in 14, we have what? 1 plus sine squared 30 degrees plus sine squared of 60 degrees. Okay, so the main thing I want you to see here, right, is what? We have a 1, sine squared theta, and sine squared of 60 degrees. I want you to see that, okay, what a coincidence, right, that we have 60 degrees and 30 degrees. What do they add up to? 90 degrees, right? So we can change one of them to be like the other function. So it could be any of them really. Like let's change this to 30, right? So let's change this guy to something of 30. So what's sine's like brother, right? It's cosine. So if we write this out, it'd be like sine of theta is equal to cosine of 90 minus theta, I believe is the formula here. I think they're called cofunction, coterminal, something like that. But basically, like, we can turn sine into a function of cosine, is what I'm trying to get at here. So here, if I had 60, right, I want to turn them into a cosine, right? So I have sine of 60 is equal to cosine of 90 minus 60. So what do I get here? I get 30. So this sine squared of 60 degrees is the same thing as cosine squared of 30 degrees. As simple as that, right? Because 60 and 30 give me 90. That's the whole thing. So here, this gives me 1 plus sine squared of 30 degrees plus cosine squared of 30 degrees. Perfect. So again, right, if I look up here, what do I have? Sine squared 30. So sine squared theta and cosine squared of 30. The same theta. So these two just kind of reduce into 1. This becomes 1. So we're left with just 1 plus 1, which gives me 2. Let's double check your answers to make sure I'm not wrong. Number 14, right? 14. 14A, yep, it gives me 2. Okay, so let's do part B over here, I guess. So this is part A. Let's do part B. So we're given 1 minus tan squared of 5 degrees plus, okay, that's too close. Let's erase 9 because we're already done with this question. And we'll start up here. Okay, so this is what, 14b. I'm given 1 minus tan squared of 5 degrees plus cosecant squared of 85 degrees. Okay, maybe that's a little too high up. I can't reach that. But basically, again, what do I want to what do I want you to see? The relationship between 85 and 5, it's 90 degrees, right? What a coincidence once again. So we're manipulating one of them to look something like these three. It could really be either of them, like it doesn't matter. Okay, so let's do tangent, I guess. Why not? So if we look at tangent, right? What's tangents? Like no, it's not this guy. So sine and cosine are like brothers, right? We also have tangent and who is it? I had to do some research right there. Fact check myself. So it's actually tan theta is equal to cotangent of 90 minus theta. So like they're like brothers. And then we're also missing, let's do secant. Secant of theta is equal to cosecant of 90 minus theta. So these are interchangeable. Like if you need to convert between one of them, it's fine. Like this could be cotangent is equal to tan of 90 minus theta. Cosecant is equal to secant of 90 minus theta. You get my drift, right? So let's change tan, right? So if we change tan of 5 degrees into terms of cotangent, 90 minus theta, or this would be 5 degrees. So what are we left with? We're left with this converts into cotangent of what? 90 minus 5 is just 85, right? 85. So let's do 1 minus cotangent of 85. So tan squared. So 1 minus cotangent squared of 85 degrees plus cosecant squared of 85 degrees. So let's go ahead and look at our good old charts, right? Or our formulas. What do we have? We have cotangent and we have a cosecant. Cotangent and cosecant. Perfect. So what we can do here is actually kind of move it over. So we have to like make space for let's change cosecant into terms of it because it's already like coded into cosecant here. So let's change this cosecant into 1 plus cosine or cotangent. Jesus. So we have 1 minus cotangent squared of 85 degrees plus what? 1 plus cotangent squared theta. Or, oh, oops, I should have changed that to 85. So this becomes 85 degrees. Cool. So now we're left with what? Oh, actually, yeah, this kind of cancels out. So let's remove this parentheses for now. So now we have what? 1 plus 1, pretty much. So negative cotangent 85, and this is plus cotangent 85, so these kind of cancel out, and we're left with what? 1 plus 1. So yeah, another 2. As simple as that. Well, not simple. This was a little complicated, I'm not going to lie. But so let's move on to the next one. 14C. What do we have? We have cosine of 70 degrees, sine of 20 degrees, plus sine of 70 degrees, cosine of 20 degrees. Okay, yet another relationship thingy, right? What do we have? We have 70, 20, 90, right? 70, 20. Yet another 90. So what are we trying to do here? We are trying to convert one of them into to the other one. Let's change cosine into terms of sine. So cosine of 70 is the same thing as sine of 20, right? Because why? Let me write it out. So let's do cosine of 70 is equal to sine of 90 minus theta, right? And our theta here is just 70. So we have what? Sine of 90 minus 70. So this becomes 20. So we have sine of 20 degrees, sine of 20 degrees yet again, plus what? We have sine 70 and cosine of 20. So here I have sine 20 degrees on like 2 terms of sine 20 degrees. So here I want to get everything into 20 degrees as well. So let's go ahead and change this sine into terms of cosine. Again, right? So let's do sine of 70 degrees equal to cosine of 90 minus theta. And our theta here is just 70 degrees. So 90 minus 70 gives me 20 again. This is cosine 20. So our sine 70 becomes our cosine 20 degrees, cosine 20 degrees yet again, because of this guy. And we're left with what? Sine 20 degrees plus cosine 20 degrees, cosine 20 degrees. Also known as, we're pretty much just combining the two. So we have sine squared of 20 degrees because we're multiplying them together, plus cosine squared of 20 degrees. And what does that look similar to? Boom! We have what? Sine squared theta plus cosine squared theta. They're the same angle, right? We have sine squared 20 and cosine squared 20. Look at that, right? Simple as that. So these combine into just one. There we have it, folks. Okay, so this is the remainder of chapter 5. Pretty much just a bunch of like trig function stuff. So let's start off with number 18. So you're going to have questions like this. I think in the written portion, like you'll require a diagram and stuff. You'll see here. So this is 18a. We're finding the exact value of the indicated trig function, basically. So we're given cosine of theta is equal to 4 over 7, where tan theta is less than 0, and we want to find sine theta. Okay, so what the hell does this mean? So let's look at the clues, right? We have what? Tan theta is equal to, or it's negative, basically it's saying here, right? And our cosine is positive. So we're in some sort of like, some sort of quadrant where cosine is positive and our, our sine is negative. Wow. So let's draw our good old, all students take calculus, right? So all functions here are positive. Sine is positive here. We want to find where sine is negative. Tan is positive here. We're given that tan is negative. Can't be here, can't be here, can't be here. We're left with good old quadrant 4. So if we know it's quadrant 4, let's go ahead and draw a triangle. So I always draw the triangles in their respective orientation. So this one is a quadrant 4. So my angle goes here. So my theta is here. And then my right triangle goes here. And we go on. So cosine here is what? 4 over 7. What's cosine again? SOHCAHTOA. SOHCAHTOA. Oops. TOA, right? So we have what? Adjacent over hypotenuse. Adjacent over hypotenuse. Adjacent over hypotenuse. 4, 7. Boom. What's remaining? Just our opposite, right? Or, yeah, let's just call them opposite. So we want to find sine. So what's sine again? Sine is opposite over adjacent. Opposite over, oops. Opposite over hypotenuse. Opposite over hypotenuse. So let's call them x, right? So how do we find x? Well, good old Pythagorean theorem, right? So a squared plus b squared equal to c squared. So let's say this is a. So we have 4 squared plus b squared equals 7 squared. So always know that hypotenuse is c, right? Because that's just how it goes. Longest side is c. He's always by himself. 4 squared, 16 plus b squared equals 7 squared. This is 49. So let's move it over. B squared equals 49 minus 16. What is that? Oh my god. All right, and so continue on. So let's do question 20 now. So I'm on 20b. So this one gets a little tricky because it's tan. So 7 pi over 6. So tan, we know from SOHCAHTOA, right? Like tan is like opposite over adjacent. We want to consider tan into terms of like sine and cosine now. So tan, let's do tan theta is just equal to sine of that over this. So sine over cosine or y over x, right? So for this one, let's do our little grid, right? So we have 0. Wait, what am I looking for? Oh, right, this. 0, we have 0, pi over 2, pi, and 3 pi over 2. So pi, in terms of like pi over 6 stuff, right? So this would be like 6 pi over 6. And this is like 9 pi over 6, something like that. So here, 7 pi over 6 lands somewhere here. So let's draw a little angle here. So 7 pi over 6. So now what I can do here is like, since this is 6 pi over 6, I'm left with an angle here of pi over 6. This angle is equivalent to pi over 6. So let's do this. So we have tan of pi over 6 is equal to sine of pi over 6 over cosine pi over 6. So now, if I use my little mnemonic, right, I have sine 1, 2, 3, cosine 3, 2, 1. So we have pi over 6, pi over 4, pi over 3. pi over 6, pi over 6. So I have here sine is equal to 1. So let's stand over here. So I have 1/2 on top over what? Cosine of pi over 6 is square root of 3 over 2. Square root of 3 over 2. So when we have a fraction over a fraction, what I can do is just 1/2 times, flip this around. I think it's called reciprocal, if I'm not mistaken. So this is 2 over square root of 3, and multiply across now. So now I'm left with 2 over 2 square root of 3. Cancel these out. I'm left with 1 over radical 3. But now I got to rationalize. I think some professors don't mind the radical on the bottom. I personally don't do it, so I'm just going to rationalize here. Rationalize just means take our radical and multiply it times top and bottom. So like that, multiply across, we're left with radical 3 over positive 3. Because the two radicals here cancel out, and we're just left with 3 on the inside. So here, I know it looks like a lot, right? But basically tan is just equal to radical 3 over 3. In this case, let's do E now. So E is cosine of 270 degrees. Okay, so just do another checklist. We have 0, 90, 180, and 270. 270 is right here. Boom, right on the dot, right? 270. So on the grid, right, let's say we're graphing, where are we right now? We're on x equals 0, and my y, we know it's equal to 1 because why? It's a circle, and the radius is always 1 for unit circle. So here, my point is going to be 0 and negative 1. So cosine is what? My x, right? So here is equal to 0. Let's knock out a couple questions for 21. So let's do 21, let's do A. So we have tan of pi. So again, checklist, right? 0, pi over 2 pi. So what's my coordinates of pi again? It's negative 1, 0. Because we're on the y equals 0 and negative 1. Boom. Negative 1, 0. So tan is also sine over cosine. So my sine here is what? 0 over 1. So 0 divided by anything is just 0. Pretty much everything else is like that for 21. So it's not that bad. Like, just know like our 4 quadrants and the lines, right? So that's the end of that. I wish you guys the best of luck. I hope this helped a lot. And yeah, best of luck in your exams, guys. Peace.